let's start up. Today, I want to take about 10 minutes at the beginning to talk about bias and variance, and then spend the rest of the lecture beginning our coverage of graphical models and Bayes nets. So the reason I want to start, though, with bias and variance is it's a term that we've kind of used throughout the semester, but we haven't really talked about it in quite a precise way. And I want to do that. The reason I want to do it at this point in the course is that it fits right in with the last 3 lectures. So if you think about, if you translate into simple English statements some of the things we've learned from the last 3 lectures on computational learning theory, you see that we learned things like there is a fundamental relation, which we can characterize quantitatively, between the complexity of a set of hypotheses that the learner is considering. And in fact, we talked about 3 ways of characterizing the complexity of those hypotheses. First, we talked about just how many distinct hypotheses are there. Then we talked about the VC dimension. Then we talked about the Rademacher complexity. But there are all ways of characterizing how complex the set of hypotheses is that a learner is considering. And so what kind of the fundamental thing that we learned from the last 3 lectures is that there is a fundamental constraint that any learning system, including your brain and mine, must abide by, that relates the complexity of that hypothesis space to the number of training examples seen and the probability that given that many training examples drawn randomly from P of X, that we will succeed in learning a hypothesis whose true error can be bounded by its error over the training set. That's fundamentally the question we've been talking about for 3 lectures, and we looked at it in different angles. And it turns out bias and variance is the statistician's language for talking about quite similar notions. And so I want to just go through that. So some of you, let me ask, before I put that slide up, how many people could have written down the definition of statistical bias? Okay, good. So it's good that we're covering this. Here's the statistician's definition of bias and variance. So suppose we have some parameter we're trying to estimate, like, we can go back to our old example of a coin flip, and we're trying to estimate the parameter that defines the probability that this Bernoulli variable, the outcome of a coin flip, will turn out to be heads. That could be an example. So given that we have some parameter theta we're trying to estimate, and given that we have some algorithm that comes up with an estimate for that, I'll call the estimate theta hat, then the bias of that algorithm or that estimator is defined simply as the difference between the expected value of that estimate, if we were the expected value of that estimate, and the true value of theta. So for example, if I say my estimator, given a coin, and I want to estimate theta probability of heads, if I say my estimator is that I'm going to flip this coin exactly 6 times, count the number of heads, count the number of tails, and estimate, this will be our maximum likelihood estimate, estimate theta as simply the count of total number of heads out of 6 over the sum of heads and tails. That'll of course be 6 in our case. Then I could say, well, this is my estimator. It's this algorithm that I'm using, flipping 6 times and then counting the fraction of heads. That'll be my estimate for theta. Then what bias is defined as is the difference between the true value of theta. Suppose, for example, that theta in fact equals 0.5. It's the difference between the true value of theta and the expected outcome of that random estimator. I say random estimator because if I define my estimator as it's the algorithm where I'm going to flip the coin exactly 6 times and then count the fraction of heads, and that's going to be my estimate, then of course that estimate itself is a random variable. If I run that experiment over and over, each time flipping 6 times, I could get sometimes 3 out of 3, 4 out of 6, 2 out of 6. But its expected value, averaged over many, many such attempts, it turns out, in the case of this estimator, the expected value is exactly theta. You can prove that. We're not going to here today. It's a good thing to prove to yourself. It's not a difficult proof. But because of that, we'd say that for this estimator of the Bernoulli variable theta, the bias, the difference between its expected outcome and the true value, is 0. It's 0 for this guy, because the expected value of this estimate is in fact theta. Now, that's the definition of bias. Variance refers to, if I run that experiment many times, what will be the variance? How much will the outcome of the experiment, the outcome of the draw of this random variable, vary about its expected value? And that's what the definition of variance is saying. Here's the expected value of the estimate. If I were to flip the coin 6 times, many, many different times, the expected value, I've already told you, is theta in the case of this estimator. But in general, for some other estimator, like maybe the map estimator, might not be theta. But the variance is defined simply as how much, on average, or what's the expected variance difference between the outcome of the experiment and its expected value. Okay, so for my estimator, which is the MLE estimate, the expected value of theta hat, MLE, is theta. And so the bias is 0. And so then the variance becomes then, so the variance for theta MLE just becomes the expected difference between its outcome on any given example and its expected value, which we just agreed is theta. Squared. Thank you. Harder to say than you think. Squared. Okay? So that's the definition of bias and variance. It turns out you can also prove that for theta MLE, the variance is equal to this, where these thetas are the true value of theta. But the expected difference squared between our estimate and a true value, or more generally, the estimate and its expected value, for a Bernoulli variable, Bernoulli theta is that. And so n here, what's n? N is the number of coin flips I'm doing. So this is, I'll just say, number of coin flips. And so this is kind of interesting. This puts quantitatively what we already have as an intuition in our head, that if you want a reliable estimate of theta, that is an estimate that's going to be very close to its true value, then you ought to really flip that coin 600 times or instead of 6, if you can. Because, the outcome is going to be much closer to the truth. Well, this tells us, in fact, how much closer it's going to be. It's going to be closer, it's going to converge as 1 over n, 1 over the number of coin flips. So if I want to cut the variance in half, the variance is, one other way to think about the variance is it's, at least in this case, it's really the squared error in our estimate. Theta is the truth for this case. If we're interested in what's the squared error I'm going to get trying to estimate the true theta, that is what the variance is in this case. And so this tells us that that squared error is going to drop as 1 over n. So if I want it to go down by a factor of 2, I just flip the coin twice as many times. See, now you can see how this is starting to relate to what we talked about the last 3 lectures, because in the last 3 we're talking about, well, how does the difference between the true error of the output hypothesis and the measured error over the training set, how does that difference shrink over time? It's not quite the same thing as variance here. But you can see we're trying to get at the same notion of how does the volume of training data influence the error. And the key difference here is that here, when we talk about estimating parameters, that's exactly how bias and variance are defined. It's the bias typically defined as these quantities where the estimate that we're trying to come up with is a numerical value for a parameter. And in the past 3 lectures, what we're talking about was the convergence when the thing we're trying to estimate is not a single parameter, but a whole function. Right? That's what those hypotheses were. They were classifiers. And we're trying to tell how quickly the classifier that our learner will pick will converge to the best one.
And also the estimate was stronger because there's a high probability you are close. So the high probability the estimate is close to the truth.
That's right.
It's only a variance, it's a weaker.
That's right. So that's a good point. We were also forced to kind of hedge the thing that we proved by saying this is only probabilistically the case. Remember, the actual proof, the actual statements we made were with probability 1 minus delta.
Very, very high.
Pardon me?
Very, very high. With very, very high probability. It was with high probability.
With high probability, but with probability 1 minus delta, in fact, in the expression that we had, that we can get error within epsilon if we have m of these examples. And then, of course, we can make delta as small as we want, but that'll mean that we have to use number of examples higher.
So we have to say it's a stronger statement, right? Because here I was saying only the variance of the estimate is small, but then we are saying very, very, very high probability you are actually close to the true value.
That's what you said, but that's not what this is saying.
Yeah. So, but those statements are stronger, I think.
Yeah, that's right. In a sense, we can make those statements are stronger because here we're just characterizing this is the point. Here we're just characterizing the variance of a distribution. There we were saying, well, if you want your error to be only epsilon, and you want the probability of that happening to be at least 1 minus delta, then here's how many examples. So it was a kind of a more general, more complete characterization of how the number of training examples influences error. And here, in a sense, we're just talking about the variance. In fact, if we did, let's say, run the experiment of flipping a coin exactly 6 times, many, many times, then we might see the outcome of the experiment, that is our estimate for theta, might look kind of like this. In fact, it'll follow what's called a binomial distribution, which, if n is big enough, looks a lot like a Gaussian distribution. But it'll look like this, where this is theta itself. Well, you get the idea. That's theta itself. and our outcome, which is theta hat, our estimate. And this is the probability of getting that. Probability of observing theta hat as the outcome of our experiment. Then we'll see, well, it's most probable that what we'll observe is a theta hat which is equal to theta. And, but it's possible with non-zero probability that we'll get a different estimate. And the variance is simply, this is sigma. The variance is simply sigma squared. So this variance is really characterizing how wide that distribution is. That is, how much probability is there that theta hat, our estimate, will actually be very far from its expected value, theta. Okay, so it's just a different result, but you can see kind of at the abstract level that's really trying to get at the same fundamental question of how does learning improve, in this case, a very simple form of learning of the value of some parameter, but how does it improve as we increase the amount of training data that we use? Okay, comments, questions? Okay, so then let me ask you. Suppose I have two different estimators, the one we just talked about and the one we talked about in lecture 4. I'm just making that up. I don't remember which lecture it was. When we talked about map estimates, where we said, well, we could use the maximum likelihood estimate. That is, we can take the observed number of heads and the observed number of tails and just look at the fraction. Or we could add in some hallucinated beta minus 1 heads and beta, that should be a minus, beta 0 minus 1 tails. And these betas were our way of characterizing our prior assumption about what theta might be. Remember? Okay, so let me ask you, given what you now know from the previous slide, you can answer the question, which of these has a higher bias? Map. And why is that?
Because there is a hallucinated beta, and this beta doesn't equal to the truth.
Right, exactly. And I'm going to ask your name.
You can call me William.
William? Okay, thank you, William. William is exactly dead on correct. His argument was this has higher bias than this because, well, for starters, this has zero bias. We just said that. But this this does not have zero bias because the priors that we made up might not be consistent with what theta really is. And as we talked about before, so that means if I flip the coin only 6 times, and suppose I use beta 1 equals 10, and 10 and 2, because I think it's 10/12 likely to end up heads, or 9/10. Then if I'm wrong about that prior, then I'm not going to find that when I run this experiment flipping the coin 6 times, I'm not going to find that its expected value is in fact equal to theta, because I'm relying on my priors, which might be wrong. Good. So the one that has this has bias 0. This has bias, I don't know how much it is, but it's greater than 0. Which one has lower variance? Variance, remember, is how much the outcome of one of those experiments will vary from its expected value.
Does it depend on the size of the n?
Depends on the size of n, right. So let's say for finite n. Actually, to make the question concrete, let me say n equals 6. I'm going to flip it 6 times. Yes?
The same because the algorithm is sort of the same.
Well, the algorithm is the same, except that here I'm using only the observed 6 coin flips. Here I'm using the 6 coin flips plus some imaginary flips I made up in advance. Right. So this one actually has lower variance, right? Because my betas are going to be the same every time I run the experiment. I made those up in advance. And the only thing that will vary will be the alphas. And therefore, this fraction will vary less than this fraction. Okay. And this is generally the case that we find. So here the variance, we already said, is 1 minus theta times theta over n. And here, I'll just say the variance is less. Because I don't know what the right quantity is, but you could figure that out. Okay, so, and intuitively, this should make sense. Yes? Is what a continuous function?
Would you say you'd be able to compute the bias and variance of that estimate as a function of the beta value?
Yes, I'm saying that, in fact, there's a closed form formula for the variance of theta MLE, which is this, where this is the true value of theta, not our estimate.
Is there one for theta?
Oh, is there one for this? My guess is there's one for this, but it's a function both of theta and of betas, beta 1 and beta 0. So that's what I recommend you work out in your own time. Okay, so this is a very quantitative way of characterizing the situation. Yes? Sorry?
I was going to ask about the bias. So if we, I don't know, increase n, even in the case of norm, doesn't it converge to the true distribution?
Yes, very good, very good. What is your name? Sorry? Sweta. So that's a very astute observation. This statement and this statement really depend on n. What I should say is the bias is greater than 0 if n is not infinite. But as n goes to infinity, we talked about this before. As n goes to infinity, the map estimate converges to this because the betas become inconsequential, the alphas dominate. And so if they're going to converge to the same thing, then what I could say more properly is that theta MLE has a 0 bias for all n. And theta map has a bias greater than 0 for finite n. As n approaches infinity, its bias approaches 0 too. That's just another way of saying the bigger the alphas are, given that the betas are a constant we picked in advance, the less it matters what those betas are. And as alphas go toward infinity, then the bias goes to 0. And then their variances also converge. Again, because the alphas are the only thing that matter as you go toward infinity. Okay? So these two notions, bias and variance, are often the way that we characterize the error that we expect for any particular parameter estimator that we make. In a way, there are two different sources of error. We could have a biased estimator, like this one, and we can talk about the variance of the estimator. And for any given any given estimate that we make, I flip the coin 6 times and I make an estimate, the error that I'm going to see is going to be some function of both the bias of that estimator and its variance. And that's why these notions are fundamental in statistics. And, you know, informally, it's kind of the same thing when we train a decision tree thing, right? We were talking last time about structural model selection. For example, should we use a class of hypotheses of decision trees of depth 1, or a bigger class of hypotheses that could go up to depth 2, or an even bigger one that goes to depth n? And we saw a result that tied the VC dimension of those different hypothesis classes to the epsilon delta number of training examples. And that gave us a way of trying to minimize a bound on the difference between the training error and the test error. But in a way, the choice of which hypothesis class, decision trees of depth 2 or depth n, was in a way setting the bias, what I think of as the bias of our learner. Bias in the sense that if we're only considering decision trees of depth 2, but the true function is described by a decision tree of depth 5, we're not even going to be able to represent the correct function. And so it's biased in the sense that even if we have an infinite training set, we're not going to get a perfect characterization of that function. And then M, the number of training examples, which we denoted M the last lecture, and I'm calling N here. That was actually reducing, in a sense, the variance of our choice of the output of the learner. If we use a very big N, M or N, then we found we get a function whose difference between training performance and true error could be shrunk arbitrarily as we increase N. And that was really the variant, the analog of variance here. So it turns out we can make this even more quantitative. If we go back to our linear regression problem we talked about before, remember? We talked about learning a function where we're going to observe some y's, and the y's are produced by some deterministic function of x plus zero mean Gaussian noise. We talked about that. And in linear regression, we said, okay, we're going to estimate y as a simple linear function, for example. Maybe like that. Well, we can ask, what is the expected error that we're going to get if we train over and over on data sets of a particular size? Let's call those data sets D, maybe six training examples. But we could pick 6 training examples from the underlying distribution many different times, just like we could flip that coin 6 times repeatedly. So we could get different training sets. And we're interested in what's the expected error of our function over those different random draws of 6 training examples. Okay. Now I realize what I should have said here is h of x is the function I'll say we're learning. So then we could write that out and say, well, the expected squared error is just the true output, the y we're really going to observe. The difference between that and our hypothesis that we learn, h, just the square of that. And we want to integrate that over all the possible values of x and y. Remember, by the chain rule, this is just p of xy. So if I say, well, what's the expected prediction error I'm going to get now for a randomly drawn x that I'm predicting after I train on a randomly drawn training sample, d of a particular size, then here's the expression that defines that. And it turns out, we won't go through the arithmetic here, but we can starting with that expression, go through and factor that into the sum of 3 terms, which will look strikingly like the square of the bias, the variance, and something that I'll call the unavoidable error. The unavoidable error is simply due to the fact that, given that this is my model, I could draw a plot here of f of x. Let me instead plot y. I could plot y versus x. And if this is f of x, then my model says that for any given x, what I'm going to observe is f of x plus some random Gaussian noise around that. Right? So for example, if I use this particular x, then f of x is just this value. That's what I'll see, oops, plus whatever the random noise is. And that random noise will be centered at y. It'll be zero mean Gaussian noise. So the actual y that I'll observe will be sampled from a Gaussian distribution centered at f of x. So the unavoidable error is even if I learn my W0 and W1 perfectly, so that I perfectly model f of x, I still won't perfectly predict every y because every observed y has noise added. And so what will be my mean squared error? If I have a perfect W0, W1 that perfectly model f of x, but my y's are observed with Gaussian noise with standard deviation sigma and therefore variance sigma squared? Sigma squared. Right, so my squared error will be just sigma squared. It's the variance of this distribution. So you see what I mean by unavoidable? You can't do better than learn f of x perfectly. But even if you do, you're not going to predict the y values perfectly because they have random IID, independent, identically distributed noise for every y that we see. Okay, so that's unavoidable error. Even if we have infinite training data and a hypothesis space that actually contains the correct f of x, we're still never going to have error less than the noise. Yes?
Is there a way to predict the sigma, the noise?
Yeah, that's interesting. Is there a way to predict the sigma? What do you think?
Predict the confidence
Predict a confidence interval on what quantity?
On our current distribution, which, I mean, the current variance basically, we can predict, I mean, we can basically have a confidence interval or make a prediction of risk.
That's right, that's good. So we can in fact predict confidence intervals around here, which will give us the information about theta. I guess one simple way to, here's the problem. We can predict confidence intervals, but we won't know that those are due just to the unavoidable error. If we have infinite training data and we know that it really is a linear function we're trying to learn, then we can know that we have learned f of x, and then we can figure out what sigma is by just looking at the data and how much it varies around f of x. But if we have finite data, we don't know how much of our error is due to this unavoidable thing versus just learning the wrong function. So we can compute the confidence intervals, but to break it out as an assignment to what the actual noise influence is a little trickier. But let's finish this off by looking at the full thing. So it turns out, here again is our expression about the expected squared error between our learned hypothesis h and the true f of x. It turns out you can factor that into 3 terms, which I'll call the unavoidable error, that's our sigma squared, just the noise influence, plus a term which is effectively the bias. Remember, the bias that we defined for our coin flip was just the difference between the expected estimate. In this case, it's an estimate of y given x instead of an estimate of the coin flip probability. But still, we could talk about what's our expected prediction for y versus the true observed y and the square of that. And again, when I talk about the expected prediction for y, I'm talking about the expected value taken over different training data sets of size 6 examples, say. So there's our bias term again, with a square on it. Plus, here's another term. It turns out that that integral up there, which is our definition of the expected error, is the sum of sigma squared, the noise, unavoidable error, plus this term, plus this term. This term is exactly, again, the variance, just as this is the bias. Remember, the variance was how much do we expect the outcome of our estimator to differ from its expected value. Okay? So I think this is beautiful because what it does is it takes that first slide where we're talking about the statistical notions of bias and variance when we estimate, say, the probability, some particular parameter. And here we can map that into function approximation. And we can talk about the expected error in the predictions made by our learned function, assuming it was learned by some random set of training data of a particular size. And it turns out beautifully to factor into these three things: the unavoidable error plus the bias squared plus the variance. So these things are actually fundamentally related and they're very similar notions. So see, I hope that was worth it. But I think this is pretty fundamental. This is about as fundamental as we're going to get in this course. These are constraints that information theoretically, statistically, you cannot overcome if you are a learning system or your program is. And so this is kind of at the heart of the statistical computational basis for even doing machine learning. Okay, so what I want you to know from all that, just know about bias and variance, and that last example you saw showed that the expected error in the predictions made by learned functions can also be factored into terms that basically reflect a bias and variance style definition. Yes?
So the previous slide, I somehow felt that the f of x should be replaced by y because...
Yeah, so did I when I was saying it. So I'm going to do that, but I thought the same thing. I thought this really should be y, not f of x. And they're not identical because of that. Thank you. I think that is what I should have there. Now I'll tell you that I took this from Bishop's chapter, which I'm pretty sure says f of x, but I got to agree with you. I think it really should be y. That's the only way that the unavoidable error even gets in there. I guess without the unavoidable error, we could just, if it was really f of x, it would just be these two terms. There would be no unavoidable error. Thank you. All right. So, any other comments, questions about bias, variance, how all this? Okay, these things are all kind of different phases of overfitting and choosing a good hypothesis space and how to play the trade-off between volume of training data available and how complex a set of things and what kind of priors to put on in addition to the data. There's this big trade-off, right? And so that's what really bias, variance, and the last three lectures were talking about. Okay, then I'm going to move on to a different topic which you will recognize very well because it'll look a lot like naive Bayes on steroids. We're going to talk about Bayes nets, graphical models. And I have to admit, this is one of my favorite topics. It's back to the idea of we want to build probabilistic function approximations. We want to learn things that predict y from x or other things from other things, but probabilistically. And we saw when we covered naive Bayes that conditional independence assumptions are incredibly useful to write practical systems. But in the back of our heads, we were always a little nervous about making these draconian, extreme, not really validated, conditional independence assumptions. So graphical models is the generalization of naive Bayes to where we just make a set of explicit independence assumptions, but we don't have to say that, for example, every x sub I is conditionally independent of every x sub j given y. That's making a whole bunch of conditional independence assumptions. In many cases, we really just want to make certain conditional independence assumptions and not others. And Bayes nets is a framework that allows us to do that in a way that leads to very useful learning algorithms. So that's what we're doing. One way to think about graphical models, which I'm using as a synonym for Bayes nets, is that they're a way of drawing a graph with nodes and edges that encodes a set of conditional independence assumptions. And that graph structure plus a bunch of parameters that we're going to have to estimate from the training data, learn from the training data, then define a joint probability distribution over a set of variables. And there are really two dominant types of graphical models that you'll see in the literature. We're going to talk about directed graphical models, also known as Bayes nets. You'll also see in the literature some work on undirected graphs. That just means the edges do or don't have direction on them. And both of these are very useful. In this course, we're going to focus on this one. Okay, so just to remind us all, we've talked about this quite a bit, but remember the definition of conditional independence is simply that if I have random variables x, y, and z, then I will say that x is independent, conditionally independent, of the value of y given the value of z if this expression holds. That is, the probability that x takes on a value given y and z is the same if I ignore y. So that's what it means to say x is conditionally independent of y given z. Okay, and we talked, for example, if x could be thunder, y could be rain, z could be lightning. If we don't know whether there's thunder, all we really need to know is lightning. Doesn't really matter what rain is. Okay, just to review. Sometimes you'll also hear people talk about marginal independence. It's just unconditional independence. So just to be complete, the definition of marginal independence is that the joint probability of x and y taking on their values is just the product of each of them independently taking on those values. Okay, so that's just review. So now let's talk about Bayes nets. Suppose I have random variables like these. Suppose here are 8 different Boolean random variables. They can have value 0 or 1. X1 is, did I visit Asia this month? X2 is, am I a smoker? X3 is, do I have tuberculosis? And so forth. We might be interested, for example, in some medical application in relating these different variables in order to, for example, predict whether I have tuberculosis or cancer. There are some medical results in here too as random variables. If we were to sit down and study this problem, we might say, well, some of these things depend on others. For example, lung cancer, we know, depends on whether you smoke. That's probabilistically influenced by whether you smoke. And whether you get cancer, of course, is determined by whether, or influenced by whether you have lung cancer, and so forth. Maybe if you visit Asia, where there's a higher preponderance of tuberculosis, that might influence too. So we could relate these variables by drawing those kind of dependencies among them. And if we did, we would have a Bayes net. Well, we'd have part one of the two-part Bayes net. Part one is really this, drawing a graph among a set of random variables. And then part two is to associate with each of these nodes a set of probability terms that tell how its value depends on its immediate parents. Then we'd have a full Bayes net. Okay? And one way to think about a Bayes net is that it fundamentally is tied to the chain rule. So remember when we talked about joint probability distributions over collections of random variables, we talked about the chain rule. So for example, if I have these nodes which I call x1 through x8 in my graph, then the chain rule tells me in general that I can factor that joint distribution in a particular way. But this Bayes net I'm going to interpret as telling me that instead I can factor it in the way shown in red. And if you look carefully at that way shown in red, what you'll notice is all it's saying is that for each variable here, I have one term in my red expression, giving the probability of that variable conditioned on something. And in each case, the thing it's conditioned on is just the immediate parents of it in this graph. So for example, that last term's the probability of x8 given x5 and x6. That's x8 given x5 and x6. So the rule for a Bayes net is that if you write down a graph and directed edges among variables, effectively what we interpret that is as you saying, I can factor the joint distribution over all those variables into the product of n terms. If there are n variables, there will be exactly n terms. And each of those terms is the conditional probability of one of the nodes, one of the variables in the graph, given just its immediate parents. So to be absolutely precise then, here is my definition that you should know this definition by the midterm. It says a Bayes network, it represents a joint probability distribution over a collection of random variables. The network itself is just a directed acyclic graph, no loops, no directed loops. You can have undirected loops, that's fine. Each node in the graph represents one of your random variables. So if you have n variables, you'll have n nodes. Edges denote dependencies among those variables. And for each node x sub I, its conditional probability distribution simply defines the conditional probability of xi given its immediate parents. And I'm using PA of x to mean just the immediate parents of x in the graph. And then the joint distribution over the n variables in the graph is simply defined to be the product over I being the index for each variable of all these conditional probability distributions. Okay. So to define a Bayes net again, you just need to define a graph and each of the conditional probability distributions for each node in that graph. Okay, so let's look at an example to ground this out. So here are 5 random variables. Again, these are Boolean variables. In general, they won't have to be, but many of the examples we will use Boolean random variables just to keep the arithmetic easy. But yes or no, there could be storm clouds. Yes or no, I could be windsurfing. Yes or no, it could be raining. And so here are 5 random variables that I might use to represent a data set where each example had a value for each of these 5 variables. Today I'm not windsurfing. There's no rain. There's no lightning. There's no thunder. I don't even know whether there's storm clouds. Okay. So this Bayes net, meaning this graph plus, oh, here's the conditional probability distribution. So for each of these nodes, we also have to write its conditional distribution saying how its value is determined by its immediate parents. And so here's the one for windsurf. And its immediate parents are lightning and rain, which could be true or false. So here are the 4 possibilities for lightning and rain. And the conditional probability distribution on the Boolean variable windsurf maybe could be defined. Here's a potential definition of that conditional probability distribution, right? Saying if it's not lightning and it's not rain, then there's a 90% chance that I'll be windsurfing. And the probability that I won't be windsurfing in that condition, therefore, is just 1 minus this. Okay? So if I want to represent this conditional probability distribution, how many parameters do I need? Yes? 4. Right. I need, if I specify these 4 numbers, then this column is just 1 minus this column. But these are all 4 independent parameters I have to specify to define that conditional distribution, right? Okay, and then given basically this graph and a definition like this for each node, I now have the joint distribution over all variables, meaning that for any given assignment, like yes, no, no, yes, no, I could just solve for what's the probability of that joint assignment by multiplying together the entries, the 1, 2, 3, 4, 5 entries in these 5 conditional distributions. I just pick out the correct one for what I just said the assignment was here, and I just multiply that times the other 5. So it's very easy, given a Bayes net, to calculate the probability of any joint assignment to all the variables in the Bayes net. If you have n variables, it's the product of n numbers. So it's really nice to go from a Bayes net to the calculation of a full joint assignment of variables. Okay, what can we say about conditional independence here? So I said that Bayes nets were nice because they're a way of easing off the draconian conditional independence assumptions made by naive Bayes. It's true. But that leads to the question, well then, what are the conditional independence assumptions implied by this graph? So one way, there are a couple ways of looking at this, but for now I'll just give you one important rule. We can say this: each node is conditionally independent of its non-descendants given only its immediate parents. So windsurf is conditionally independent of its non-descendants given its immediate parents, lightning and rain. So windsurf, given lightning and rain, is conditionally independent of thunder. That's what that rule is saying, right? You can read these conditional independencies directly off the graph according to that rule. This rule is not complete. It doesn't tell you every conditional independency, but it tells you some. So it's correct, it's just not. The rule gives you a sufficient condition for conditional independence. It's not a necessary condition. So tell me, what's another thing that windsurf is conditionally independent of given lightning and rain? Storm clouds, right. That's another non-descendant. How about rain? What is rain conditionally? Give me a conditional independent statement about rain. Rain is conditionally independent of x given y. What's an x and a y? Yes?
Lightning and thunder.
So rain is conditionally independent of lightning given storm clouds. Right. Right? Lightning is a non-descendant. Did I say lightning or thunder? Rain is conditionally independent of thunder given storm clouds, and it's also conditionally independent of lightning given storm clouds. Okay. So you can just read these off. So that's a sense in which Bayes nets encode conditional independencies. How would you prove that? If we give you a homework assignment that said, prove from the definition of Bayes nets that for this Bayes net, rain is conditionally independent of thunder given storm clouds. How would you even proceed to work on that homework? You have to go back to the definition of Bayes nets, right? What's the definition? What I would do is I would say, well, we define Bayes nets by saying the joint distribution over these 5 variables can be factored into those particular 5 terms. And therefore, I would write that down, and then I would show that if you factor it that way, indeed, the probability that rain takes on a 1 or a 0 is independent of lightning given the value of storm clouds. So I just go back, write out the definition of the joint distribution in terms of the factors, the n factors, and I could prove it. You could prove it. Okay, so to be precise about our terminology, as I mentioned, we're using parents to indicate just the immediate parents of some random variable. In general, I use the word antecedents to mean the parents and the parents of the parents and etc. And children to mean the immediate children, and descendants to mean the transitive closure of immediate children, the children of the children, etc. Okay. So just some terminology that we'll use throughout the next 3 lectures. Okay, so now let's look. I mentioned several times that Bayes nets are well understood by thinking about their relationship to the joint distribution and the chain rule. So remember the chain rule? Remember the chain rule? We introduced it by saying the probability of x1 and x2 equals the probability of x1 given x2 times the probability of x2. But the chain rule actually generalizes to any conjunction of variables. The probability of SL, R, T, and W taking on some value, according to the chain rule with no conditional independence assumptions, just a fact about probability. Chain rule tells us we can factor this into the probability of the first one times the probability of the second one given the first one times the probability of the third one given the first 2 times the probability of the fourth one given the first 3 and the probability of the last one given all the others. That's just chain rule, nothing there, no assumptions, it's just the nature of probability. But in a Bayes net, we're saying, no, we're not going to represent it this way. We're defining a Bayes net to say that the joint distribution is this. So what should we write down for this particular Bayes net is the factorization here. Which should I write down first? P of S. I like P of S because, right? So S has no parents. So this thing is, this quantity just turns into P of S. There are no parents. Okay, what do we write down for L? P of L given what? S. It only has one parent. Okay, what do I write for R? S. R only has one parent. What do I write for T? L. That only has one parent also. L. And what do I write for W? L and R. It's two parents. Cool. Okay, now look what we just did. We said, well, in general, with no conditional independence assumptions, we can always express a joint distribution this way. But according to the rules that we use to define a Bayes net, effectively we're saying the Bayes net, its total meaning is that instead we're going to factor it this way. And look at the difference. It's actually kind of cool. These are the same, but then things start diverging. We're saying, no, 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 no. We don't need this L. Because R is apparently conditionally independent of L given S. That's what we're saying. And similarly, we're saying, well, in this term, the only thing we need to keep is the L. Effectively, we're saying, you know, T is conditionally independent of S and R given L. T is conditionally independent of S and R given L. Remember our rule for reading these things off the graph? We said each node is conditionally independent of its non-descendants given its immediate parents. So if we go and look at T there, we could read off that it's conditionally independent of S given its immediate parent L, and that it's conditionally independent of R given its immediate parent L. Yes?
If like one of them has a parent which is also a grandparent.
A parent which is also a grandparent. Then it's so you mean if we did this? Okay, so now W would be conditionally independent of its non-descendants given its immediate parents. So that means W will be conditionally independent of T given its immediate parents, L, S, R. I guess to be precise, I should say, and is not conditionally independent of its immediate parents. So I meant that. Right, so I could say the rule is every variable is conditionally independent of its non-descendants except for its immediate parents, given its immediate parents. So that would be the more complete. Okay. Okay, I'm going to erase this because I don't want it hovering around in our slides on the website. Okay, and so just to kind of complete this, and this is maybe the most important thing to understand today about Bayes nets, is that here are a whole bunch of conditional independence assumptions being expressed simply and very clearly, very vividly, by this simple rule that says instead of factoring the joint distribution according to the chain rule, which makes no independence assumptions, when we write down a Bayes net, what we're saying is we intend instead to factor it into these simpler terms where we're leaving out things which correspond to our conditional independence assumptions. Yes?
I'm concerned about the directionality here. What does it mean, like the relationship between a parent and its immediate child? What does the directionality arrow mean?
Oh, what does the directionality arrow mean? Well, it would be nice if I could answer that, say it means causality, but it doesn't. In fact, as we'll see, the direction of the arrow really means nothing. So I can represent, well, we're going to see a couple examples in a few slides where you'll see that we can, for the same joint distribution and the same set of assumptions, we can write multiple Bayes nets that have the same meaning in terms of the factorization they provide. So another way to say that is it turns out given a factorization, it's not true that there exists a unique Bayes net that captures that. And also it's true that the arrows do not indicate causality. Although a lot of people intuitively, you know, when I introduced this and I said there are these variables and we know lung cancer is probabilistically, I hope I didn't use the word cause, but I bet I did, caused by smoking. What I should have said to be careful, are there any philosophy? To be careful, what I should have said was it depends probabilistically on whether you smoke. So causality is a dicey issue. And by the way, it's just side comment, causality is a topic where, which is becoming increasingly prominent in machine learning. And the question of, can you infer causality from a fixed data set? Very interesting question. I used to think the answer was no, but then some colleagues over in the philosophy department, like Peter Spertes and Richard Shyness and Clark Limor, showed that in fact it could be, in certain cases, inferred from data. And today I received an email from the department head of philosophy telling me that he's very excited. They just hired a new professor who will be here in the fall who specializes in machine learning approaches to studying causality. His name is Kuhn, so watch for him. But anyway, side comment, causality is a very interesting topic, but I sadly cannot say that's not what we're talking about here. Okay, so yes?
Because we're not assuming this causality, is that the reason we say non-descendants in that definition?
Sorry, I didn't hear the first part. Is that the reason we say non-descendants?
So, I mean, given this question and the discussion we just had, is that the reason we talk in the definition we write non-descendants? Because what's the relationship between the parent and the descendant?
Yeah, so we very carefully choose the word descendant or non-descendant instead of dependent or caused. And it will turn out that probabilistically, L does depend on the value of T, as we'll see. Meaning depends probabilistically in the sense that if I tell you what S, R, W, and T are, then you can solve for what's the most probable value of L. And you could see that here. You know, if we know the joint distribution, and I give you 4 of the 5 variables, you can solve for the probability, the marginal probability of just the remaining variable. And so in that sense, that value that I'd be solving for does depend on in many cases, it's descendant. Probabilistically depends on, and that's the reason really that we talk about descendant instead of dependent, because that would be. In fact, that's one of the key things. So I've watched people learn Bayes nets for a number of years now, and there are like several Zen levels. The first Zen level is this. If you get this, you're already at the first Zen level. You already understand that we can represent, Bayes net is simply a way of saying, I'm willing to make certain conditional independence assumptions, and here they are. The second Zen level is when you get to realize exactly how you can use this to answer any probability question that I ask you of the form, what's the value or the probability distribution on this subset of variables given these other the values of these other variables. And there, part of reaching that Zen level is that you start to realize that actually the value of L will depend on its descendant. And so the arrows don't mean that the parent doesn't depend. The parent, in fact, does depend on the descendant. Yes?
I have a question about assumption. Like, why they make the assumption like they only depend on their immediate parent?
Yeah. So this is, the question is a good one, is how do we come up with these assumptions in the first place? And that's an art, not a science. It's really the problem of taking a non-mathematical problem and framing it as a mathematical problem. Intuitively, you can see it's like saying, well, you know, really, I do think that given whether there are storm clouds or not, rain is probably independent of whether I'm windsurfing. So this does, I could argue on an intuitive common sense basis about why this particular conditional independence assumption seems reasonable to me. But you know, you could argue back and then we'd agree we should use a slightly different graph for this BaseNet. So the BaseNet is really just, it's a mathematical notation is what it really is. Just a way of denoting this factorization. And then the attendant with that is that it turns out the number of parameters that we have to learn from the training data goes down dramatically if we're talking about these factors instead of these factors. You can see that this one's going to, well, how many parameters will it take to represent this conditional distribution? If I use the full joint factorization and I have some training data and I want to learn to estimate for these 4 Boolean variables, the conditional the table like I have up there for W, but now for T. If I want to get the conditional probability of T given these 3 Boolean variables, how many parameters will be in the table for T? 8? I like that answer. Okay, 8, 2 to the 3. There are 8 possible joint assignments of SLR. And for each of those, I need to know the probability that T equals 1 and the probability that T equals 0, but that's just 1 minus the probability that T equals 1. So I need the first, so it will have 8 rows instead of W having 4 rows. Okay, so we need 8 parameters to do this. How many parameters here? How many parameters here to estimate the conditional probability of T given only L? 2. So you see, what we're doing here is just like in naive Bayes. When we started naive Bayes, we were justifying it by saying, oh, naive Bayes is a great idea because instead of needing for n variables 2 to the n parameters, 1 for every joint assignment of those n variables, for naive Bayes, we only needed 2n plus 1 for the prior. And here, it's going to turn out that it's more than 2n because some of these things depend on a couple variables, not just 1. But it's still going to be dramatically lower than the number here. In fact, what I want to do is end here and suggest that a good thing to do after class is just answer the question, how many parameters do I need here? By the way, that's easy to see. It's 2 to the 5. Right? You already know the joint distribution has 2 to the 5th rows in it. So when you multiply together the number of parameters here, or sorry, add together the number of the parameters here, it better be 2 to the 5 or you've got a bad problem. But then figure out how many it takes in this BaseNet, and you'll get the idea of how the parameters and the conditional independence assumptions go together to occupy a very interesting middle ground between the draconian naive Bayes classifier and the non-independence assumed joint distribution. And we can put in here sort of a whole bunch of different Bayes nets that occupy the intermediate points on that spectrum. Okay, next time we'll talk about how to do inference in these Bayes nets. Another good question to think about in the meantime is, what would a naive Bayes classifier look like if we drew it as a Bayes net?